Baby, I... All right, so today we are going to talk about perfect. Before the lecture, I always like to play some songs and with some slideshows telling about like what's the most important thing to do before doing a lecture. And I played a song Perfect, and the version that I play, you might feel like it's a little bit different from the one that you normally hear, because I think, like Ed Sheeran, he is good, but I think with the voice of like Beyonce, I think it's even better, right? So that's why we sometimes need diversity. But what does perfect really mean? Today, I'm going to talk about what does perfect mean in computer architecture class. But before we start, it's always important that we should put ourselves on the same page and knowing where we are coming from. So we are living in a world that every computer system is pretty much composed of two main types of components, processors and memory. Trust me, no matter what kind of computer you are using, you can't really rely on you cannot find a computer without these two things. So, but why we live in a world with computer look like this? Because the big picture in computer architecture is indeed the von Neumann architecture. So, not sure how many of you know the history of computers. A lot of people would contribute like the father of computers as Alan Turing, but my feeling is if you really want to talk about the design of modern computers, you probably want to talk about John von Neumann, because people like Alan Turing, they create the algorithms. But to be honest, algorithms do not have to be run on computers. Like yourself, you can run the algorithm, right? You do that a lot in your algorithm midterm or final exams. Don't you feel that way? Like you are solving the problem running the algorithm without a computer. So algorithms, they don't have to run on computers. So I won't call Turing as the father of computing. I would say he is the father of algorithm, right? So he is telling you how to solve the problem. He is the father of problem solving, but he is by no means the father of modern computer. But how about John von Neumann? He say a modern computer system should have these three components: processor and memory. And I added secondary storage here because right now it's hard to imagine a computer without secondary storage. And the use of this modern computer is when you have a program, it's either the compiler or the runtime framework generating machine code and translate your data into binary encoding. And these two things together is a program. So when you compile your program, if you have a global variable, it's already located within a binary. There is a region called data section that store those data, the initialization value. So this is the whole binary executable. And when you want to execute a program, your system, pretty much your operating system, will load this compiled executable or generated executable from your storage to the memory. And in the meantime, once we are done with that, your processor, there is a special unit called program counter, which tells where in the memory should I start executing this binary from. So based on that pointer, it will go to the memory to fetch an instruction, and based on the content of the instruction, it will prepare the input data for this instruction and then drive the correct functional units in the processor to execute that instruction. And in case the instruction needs to access memory, we will trigger additional data memory access. But why joint von Neumann architecture is so popular? The main reason is with this architecture, if I give different instruction stream in a memory, the computer can perform a totally different set of operation. So for example, your laptop can now be a machine trained machine learning model, but could also be a powerful gaming machine. You don't have to have two different processors, two different computers to make that happen. And who contribute to that? Von Neumann architecture. So a lot of people, they create program, they write program just based on the algorithm complexity contributed by a lot of theory people like Alan Turing. However, there is a very big mismatching between their imagination about what a computer is and what really a computer is. So if you just based on computation theory, you would definitely think adding a sort in front of this for loop is not going to give you any better performance. But in fact, that's not the case through the demo the last time. So on the computational complexity, and even you count the number of operations, you will feel like the left-hand side and the right-hand side, they shouldn't be any difference. However, in fact, the left-hand side is a lot better. So those are the things that computational complexity or algorithm class won't teach you. And in fact, this is what this class is going to teach you, how to write an efficient program. So, and why we want to write an efficient program? Because right now we are living in a world where our hardware is not getting faster in a way to catch the demand of real applications. So it really matters as a software programmer. We know how to maximize the utilization, how to maximize what we can get from the computer that we have. So before we start the lecture today, I wanted to watch this quick example and then tell me your thoughts by answering a question of mine. So this is a demo of using ChatGPT and Gemini to ask the question, what is computer architecture? Okay, so now I'm going to ask you this question. Please grab a few people around you and try to answer this question. Make noise, talk to people, get some friends. like based on the video. All right, what do you guys think? What do you guys think? Which side has better performance? Be careful, like this is going to be broadcast on YouTube, right? Gemini has better performance. Who said that? What's your name? What? Hugo? Okay, why? Because it ends faster. Ends faster. Okay. Other thoughts? You all agree with that? The first token is faster, but would the, well, yeah, but would the first token give you the answer already? Not really, right? How many of you, I should try to make this off record. How many of you try to write an email to like the CSE office? How many of your question can be answered by the first email? Right, you know that feeling, right? So, okay, so like sometimes when you talk about performance, it really matters that we put everyone on the same page. And like, for example, like, is UCR the best university, right? You have your own judgment, right? But like, if you talk about like best university, some people say Princeton is the best. If you are a computer scientist, you will know, like, you will definitely think MIT is the best. And then, well, like my where I graduated from, like with this Washington Monthly, they say UC San Diego is the best, which I don't 100% trust. And like even UCR, we also said we are the best in some capacity, right? So every university is the best, right? So we really need, like, all the generative AI, they tell you it's the best. So at least for now, I know there are different matrices, but at least for now, we have to put everyone on the same page when we talk about performance. So for CS203, we start with this metric as the performance, which is the end-to-end latency, how long it takes to execute a program that is that is our current default performance metric. So like Hugo said, you feel Gemini is better because it gives you the whole answer faster, right? And you said ChatGPT is better because you think you got the first token. But to be honest, in general computing, the immediate response may not be the most meaningful in most of the cases. And like even for like programs, right? If all results generated in the very beginning, they are correct, but at the end, if it's wrong, it's wrong, right? That's pretty much like your programming assignment. We check about the correctness, right? If at the end it's wrong, sorry, 0 points, right? So in computer, by default, we talk about end-to-end latency as the default performance metric. Don't ask me why, but I already tell you, because we care about the overall, the complete result rather than just the partial result. So today we are going to talk about a few topics. First of all, the definition of performance, the classic CPU performance equation, and what really affects the performance. So now we talk about that in this class. We are going to use pure instruction. So before we start the peer instruction question, make sure that you log in through the Poll Everywhere through an app, or if you have a computer, you can also use your computer, and then spend 90 seconds. And if you miss the QR code, it's on the left-hand side of the slide. And if you have a computer, there is a URL on the right-hand side. And please spend 90 seconds individually. Don't talk to anyone. I don't want to hear any voice at this moment. Try to solve the question by yourself. All right, let's take a look. Okay, the initial intuition is C. So why don't you guys go to discuss with your friends to make sure that you are on the same page why it is C. And then once you are done with your discussion, you reach a consensus, don't forget to vote again. Now I want to hear noise. Make some noise. All right, don't forget to send in your vote. No, it's not. Okay, so, well, 26 of you successfully voted. The answer is C. All right, so now, how do you guys get the answer as C? I want to hear someone explaining that, like share it with the whole classroom. This question is pretty much like letting you know what's the format of peer instruction, right? So right now you're done with the group discussion and we want to hear from all of you. Like you reach a consensus, right? We want to hear that, right? And the best thing about doing this is that if you feel shy getting the like showing the wrong answer in front of the whole group, you can say, well, my group, they say, it's not me, they say, right? All right, so can someone tell like what your friends say? How to start with that? Like for this question? Okay, what's your name?
Connor.
Connor? Okay.
I just went through like both the instructions and the cycles and tried to just calculate it just manually with math. So the processor is 4 gigahertz, which is I just did the math to get like I don't know the exact wait. So would it be 0.2? No.
Okay, first of all, right? You have done a reading quiz, did you?
Yes.
Okay, so you have read the textbook, right?
Yes.
So if we want to solve this question, what would be the first thing that should pop up in your mind?
So the performance equation.
The performance equation, what is that?
Execution time equals instruction count times average cycles per instruction times clock time.
Right. So to solve this question, we need to get all three elements, right? So you start with the cycle time because it seems the most intuitive to get, right? The cycle time is 1 over your frequency, 1 divided by 4 gigahertz is 0.25 nanoseconds. And because 1 gigahertz is typically 1 nanosecond, so divided by 4, that will be 0.25. Okay, so we still need instruction count and a CPI.
For the main, just to simplify it a little bit, the first instructions we can kind of disregard those because that's not the main loop.
Since right. Okay, so where's the main loop?
It's in the like point L3, the main loop between the jump instruction for L3 and right there. That's where the main process of your execution is going to be.
Okay, so first of all, if you don't understand this assembly, I would encourage you to go through the assigned reading again because S86 is what we are going to leave with the whole quarter. If you don't understand, I don't require you to write it from scratch. But if I give you this kind of like side-by-side comparison, you should be able, my goal is that you should understand what the right-hand side map to the left-hand side. So for the right-hand side, according to the x86 format, like this L3 column is basically a label, which is associated with the next instruction, right? And the JNE is jump not equal. If the previous comparison result is not equal to 0, you will jump back to L3. So in that way, you can pretty much imagine this is the loop body. And given that, if you have sufficient amount of loop iterations, then as what Connor said, this beginning part and the later part doesn't matter, right? So what really matters is the main part. So how many instructions are there in the main part?
5.
I can't hear you. I can't hear you. Louder. 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 No, this is not louder. Louder. Okay, awesome. Right? So how many total number of instructions do we have? 5? What's the IC? 5 billion, right? 5 times this 1 billion, right? So that's interesting, right? Like, okay. Anyway, so 5 billion instructions. What's the average CPI? 50? 50 average CPI. What's the definition of CPI? Read it out loud. Cycles per instruction, right? So how many cycles is it for a memory instruction? How many cycles is it for a branch instruction? How many cycles it takes for other instruction? Okay, so how many percentage do we have in a memory instruction? What? 20%, right? Because it's 1 out of 5, right? This move instruction is the memory instruction. If you cannot tell this, you should go back and read the assigned reading, right? So that's why I'm saying the assigned reading, it matters. And you guys are not undergrad anymore, right? Read the document, right? Like I've been working in Google, right? The IT will give you, they will, you know, they will look upon you if you don't read the document ahead of time. They don't answer you. They don't help you on site. They just tell you, go read this document, right? And you don't want people to treat you like that, right? So read the document, right? So how many branch instructions do we have? 1 out of 5, right? This is the branch instruction. So others is 1, right? So based on that, right, we could potentially get, we can potentially map this problem into the performance equation where execution time equal to instruction count times cycle per instruction times cycle time, right? So the total number of instructions we have and the average CPI, as we said, 20% are memory instructions, 20% are branch instruction that takes 2 cycles and the 60% are the remaining. So that's the average CPI. So that's how we get 2.5 seconds as the total execution time, right? So you might wonder why we have this equation. Again, if you could remember what's the big picture, it's not too difficult for you to figure out where it comes from. So this is the big picture of neural architecture. As we said, your execution time, your execution is determined by how many instructions that we have to really execute, right? So that's why it comes from the factor that how long do we need for each instruction on average, and how many instructions do we have, and the cycle time. So that's why the performance equation is defined by the execution time equal to instruction count times CPI times the cycle time. And as we previously feel, the shorter the execution time, the better the performance. So that's why performance is defined by 1 over execution time. And in this textbook in CS203, in general, in computer architecture, we talk about performance. This is the golden rule of performance defined by the end-to-end latency. There's no other definition of performance unless otherwise mentioned. So this is the performance equation. So but for this question in particular, since we have 1 billion instances between the L3 and the JNE L3, and this pieces takes 5 instructions, and within this 5, 1 is the memory, the other is 1 is the branch, and others, they are the regular instructions. So that's why you get an average CPI as 2 cycles, and the total execution time becomes 2.5 seconds. All right, so the first takeaway is the only definition of performance is the end-to-end latency. And the end-to-end latency is defined by 3 elements: instruction count, cycles per instruction, cycle time. And Now let's talk about what affects each factor in performance equation. So the first thing that I want to talk about is programming languages and performance. So a lot of people, they want to showcase, I know a lot of languages, but within this 5 programming languages, do you know which one would need the highest instruction count to just print this one line of hello world? No, this is an individual thinking question. No discussion now. Well, people give the answer pretty quick. So maybe we can make a quick wrap up. All right, the initial intuition told us, oh, okay, there are 2 answers. A lot of you think it's C, a lot of you think it's E. So why don't you guys discuss with each other, like Java or Python, which one is going to be slower? All right, sorry, one more time. All right, so based on the discussion, more of you think Java is slower now, but I want to hear some of your voice. Why do you think that way? Like, any idea? Like, why do you guys vote for Java? What's your name? Drew. Drew. More APIs? Okay. Other thoughts? Why is Java the slowest? Shaban?
Because the Java virtual machine.
Java virtual machine, but why is Java virtual machine causing to be slow? Python also have a runtime, right? Why the virtual machine is slower than a runtime?
Because there's more like kind of going on than
what is going on? I feel like I'm questioning you. Like, what's going on with the fair? Anyway. Okay, what's your name?
Nick.
Nick, what do you think?
My answer was similar to his. I imagine it would have to do with virtual machine, but I don't know the inner workings as to why it would slow down performance.
Okay, so we all have a feeling Java might be the slowest, right? But as I told you in the very beginning, this class, I want to see facts rather than arguments, right? So in computer science, we should always see facts. Otherwise, you would misunderstand more slow. You will say more slow is dead, but in fact, it's still alive, right? Like you would easily going to be fooled by a lot of people doing business, right? That's what Wall Street people would typically be fooled. And my feeling is like, okay, fooling Wall Street people is my hobby if I could. So in this class, well, I mean, some of you might be entrepreneur in the future, so I hope you learn the skills that I taught you here, so that you can fool Wall Street people, and don't forget to donate us a lot of money later. But in computer science, in computer architecture, and fortunately nowadays modern processors, they provide this performance counters, which is a spatial hardware unit that would periodically sample the performance of how your program runs. And with that, we are able to get quite a few information about the program. And how to get those values, you typically need a program with kernel access. So in Linux, like in our CS203 cluster or in my machine, we use the perfstat, which is a program helping us to get a performance counter. If you have a Mac, they also have a time profiler. And on Windows machine, you can also use Intel's vTune, which is only available for Intel processors. If you are using an AMD processor, good luck on that. And you can also create your own functions. But now let's take a look of this 5 programming languages that we have. So, like the first programming language we are going to talk about is Python. So for Python, if you want to print hello world, it's pretty simple. Print hello world, right? We love that, right? So that's why everybody loves Python. So now let's run it. And as you can see, when I run it, this perf program would generate this stats for me. So it tells us that the number of cycles it takes is about 35 million. And the number of instructions is 51 million, right? Just print one line of code. It actually took you 51 million. Ever thought about that? Right? 51 million instructions, right? So the processor runs at 5.5 gigahertz, pretty fast processor. So this is an Intel Core i7 14th generation processor. So it takes in a CPI. So one thing that I don't like about, well, so for CPI, you probably need to calculate by yourself. But here, as you can see, is somewhere around let me see, cycles per instruction, like somewhere around 0.6, right? So keep that in mind, 0.6, right? So now, Java, right? The second most, the most popular answer. To print Java, it needs like 8 lines of code, right? But a lot of people, especially like software engineering class, they like this 8 line of code because it shows you the elegance of object-oriented programming. And this elegance of object-oriented programming, how many instructions are we going to see? So first of all, if you pay attention to my command line, when I run this program, I separated the compilation part and the virtual machine part, and I only count the instructions for running the Hello World program. So now, look, how many instructions? So it was like 51 million in Python, and we already thought it's a lot. Java, 126 million. Okay, so you have more than twice instruction counts than Python. And how many, and the CPI, right, cycles per instruction, right, this is like 117 million cycles, 126 million instructions. So the CPI is around just 1. So the CPI is higher, the instruction count is higher, the same processor, right? Java has very bad performance, as you can imagine, right? The execution time, this is 0.02, right? And previously, 0.06, right? Like 3 times difference. Okay, so this is not on the list, but like as a Google alumni, we should definitely promote Go a little bit. So Go is a language, I would say it's pretty elegant and pretty C-like. It does have 2 modes, the interpreter mode. So if you check the interpreter modes, oh wow, right? 1.2 trillion right? And the performance is terrible, right? 0.31 seconds. But if we could have compiled the program into an executable, then Go becomes a very good tool. It only takes how many? 5 million instructions. This is by far the smallest instruction count we have, isn't it? Right? Like Python has like 51 million, and this one has 5 million, right? So even though the CPI is higher, but if you already drop the CPI to the number of instructions to just like 10%, then your performance is going to be around like 8 times faster, right? So which is a lot faster than Python. Now look at C++. So C++ is probably the most intensively used, one of the most intensively used programming language in production code. And that's C. It also has the object-oriented programming feature, so that's why it's used in a lot of larger projects. And as you can see, how many instructions we need? 3.7 million, right? Even better than what? Than Go, right? So that's why C++ is still used in many, many projects, because it demonstrates like so far the superior efficiency over all the programming languages that we have seen so far, even the newer ones. Okay, so I work with industry closely. So a lot of industry people, especially those doing firmware programming, they talk about Rust. So that's why I bring Rust into the picture. So take a look at Rust. Okay, it's really a good one because we bring down the instruction count to 1.6 million, right? A lot better than C++, but is Rust the best? It's the best so far, but C programming language. If I do Hello World in C programming language, how many? Just one. A lot better than all others. So if you want to spend time learning Rust, I won't prevent you from doing that. But you know, the main reason why people want to do Rust is just because they already have very restricted environment. But as you can see, if you could have learned C, that's going to be more useful, right? So as a programmer, choosing the right programming language matters, right? In fact, from the same Turing lecture that John Hennessy and David Patterson have gave in the Turing Award, this is what they give. This is the example what they gave.
That's a great chart that's out of a paper called The 20th Moon at the Top by Lysis and his colleagues at MIT. And it looks at a simple example, admittedly a simple example, matrix multiply. So we'll take the version in Python. How much faster does the version just rewritten in C run? 47 times faster.
Right, so here's the thing. The language matters. So as a programmer, you can control a lot of things, but the very first thing is that you should start with the right language. If you are sticky with Python, 47 times slower, which means 47 times more cost to your company. Like I don't know, like a lot of people think machine learning is all about Python, PyTorch. That's true if you are talking about like proof of concept. But in production, we are not going to do that. Like, believe it or not, all the core machine learning program for Gemini, they are written in pure C, not even C++. Because of what? For performance. Right? So that's why you see on the right-hand side, Gemini is a lot faster. So left-hand side, or right-hand side, right, is a lot faster because they use C. I don't know what OpenAI use because I don't know any people from OpenAI. But at least like at Google, they chose the language called C, and definitely with a lot more optimization. And the faster your code, the lower the cost of your computing, or more customer you can serve on the same computer, right? So that's the trick of Gemini. Okay, and here's the summary. So as you can see, the CPI, no matter what language you are using, and in fact, because the instruction, the x86, most of the common x86 instruction, their cycles per instruction are not going to different like in orders of a magnitude. So the CPI about like they are not different, just only by like 2 or 3-fold, two times. But if you check about the instruction count, it's actually a very different magnitude, orders of magnitude. So if you could not start with the right programming language, you're already lost. You are already lost. So for this question, Java, right? So, but some of you might be asking why Java is so slow. So let's start with the C. So as you are familiar with, when you compile your C program, it will drive a GCC compiler to generate the instructions based on the code that you are written, you wrote. And if you call external library, sometimes it's going to be linked during the runtime, and sometimes if you do static linking, they will try to embody those static library code into a binary as a single binary. So whenever you want to run a program, we just directly like run the binary, load this whole binary into the memory without any additional overhead. So that's why it's faster, because you generate a native instruction, you don't have extra step. And the problem with Python is, if you look at how Python do this, it does incur the overhead every time we have to interpret each line of code during the runtime. However, after we interpret that, it's still going to be the native x86 instruction plus the data, and then partially loaded into the memory line by line. So that's the whole philosophy as Python. And the good thing is that it's easier for debugging. But as you can tell, since the original purpose of Python is designed for debugging, it's never talking about for performance, right? So if you imagine Python can be really fast only if you are able to use other tools like Cython or some other tools to make it compiled. Otherwise, Python can never be faster. And even with Cython, you are still going to suffer a lot of wrapper overhead. So there's no way, I can say that again, there's no way your Python code is going to be faster than optimized C code, right? So now talking about Java. So a lot of people get their undergrad degree and they love to develop code in Java. And they think they are going to live with Java forever. But I want to say, if you're working in a large company like Google or Amazon, they're not going to do any project with Java. And here's the reason. If you look at how Java is designed, is basically you do have a compiler, compile your source code into Java bytecode. So what is Java bytecode? It's some kind of machine code. However, this machine code is only understood by the Java virtual machine. So when you want to run a program, you need another layer of interpretation between Java bytecode into the real machine code. So this is like a runtime translation. So some of you might be curious why this runtime translation is so slow. Because Python also does runtime translation. And in fact, when you run this Python, you also need to understand the program itself. So it sounds like Python should have higher overhead, but why Java has higher overhead? So here is the reason. So if you take a look of what kind of assembly code that Java bytecode looks like, it's pretty much like this. So I don't need you to understand the whole thing, but in fact, if you check about this instruction set architecture, you will figure out Java has no concept of registers. Java doesn't use registers at all. What does that mean is that assume your machine has a stack which you can put stuff unlimited into this stack, which we know is implemented by memory, right? But if you have done some reading, you know memory is 100 times slower than your processor. Also means that memory is 100 times slower than your register. If every of the instructions have to access memory, that's going to be really slow, right? So that's the initial assumption. And in fact, if you look at x86 instruction set architecture, we have 16 general purpose registers for you to use, and Java has no way to think about how to use them in the very beginning. Java bytecode virtual machine does have a way to implement some of the part into the memory stack using registers. However, this mismatching is always causing you some additional memory accesses and some more additional instructions just because I want to move stuff around to different stacks. And also for registers, if you want to access something, just directly go ahead and to access it. But if stack, you always have to pop and push, which needs more operations. But why Java makes such an assumption? Because in the very beginning, the design of Java is never aiming at performance, but more for portability. Like a compiled binary, they can run any machine that have some versions of Java virtual machine installed. So why small companies, they like Java? Because they can just create one binary and it will work on every machine. And for small companies that do not have a lot of engineers, they don't want to create multiple optimized version of applications. So that's why they would rather choose Java. Doesn't because Java is more efficient, just because it's more portable. And since Java virtual machine assumes no registers, that makes it easy to be adaptive to every processor architecture. Because remember, every computer has a processor, has memory. Stack on the memory. There must be a processor. Nobody say that you need to have registers. Nobody said that you need to have this many registers. So register numbers, they varies architecture by architecture. For example, ARM has 64, but x86 only have 16, right? So you cannot make that assumption. But here's the thing, different programming language can generate machine operations with different orders of magnitude performance. So the first lesson for you is try to find out which language is the best for you. And in terms of performance, there's nothing better than C, C++, or Rust. And that's why all the programming assignment, even all the assignment sample code is written in C or C++. Because as a performance programmer, if you start with the wrong place, it's never going to be performing. Now, after choosing the right programming language, how are you going to affect the performance? So you remember this demo, right? We talk about the same complexity. So why the performance is different from the left-hand side and the right-hand side? Think individually. All right, so take a look. It looks like C is the most popular answer, but you know, like what are the two in your mind may be different from what the other two that you guys have in mind. So why don't you guys discuss with each other to see, is C really the answer? maybe after discussion, you will find, oh, it's disjoint, so maybe there's only one answer or something like that. All right, let's take a quick look. Okay, a lot of you think the answer is still C. So what are the two that you guys have in mind? C.
I'm just going to say, it brought to my attention that I think I intentionally, a lot of the class read it wrong, right? I chose C because I thought it was saying the second one, not that there was two.
You said how many of the following instead of like, which one?
Yeah, I misread the question, so I think that might.
Yeah, but the question is asking how many of the following.
But yeah, I think potentially a lot of us thought it was that C.
So is that my problem?
No, it's just potentially explaining that.
So be careful, right? Like in midterm or exam or reading quizzes, a lot of you saying that, hi, I think I got right. Read the question again, right? So you think it's CPI? Other thoughts? Should be instruction count. Okay, so seeing is believing, right? So let's try to run it. So again, as we mentioned, there is performance counter. So we can again use performance counter to count that. And this time I'm using the same library that you will be using in your assignments. We are going to use this perfstat library. And then let's see if I can generate this performance counter from this two. And then let's see. So first of all, there are many ways you can generate that result. It's either from perfstat or just the performance counter. And the reason why I use the counter here is because we want to forego this initialization part. So a random number generation actually costs a lot. So here is the generated result. Is there any significant difference in instruction count? No, right? So instruction count is not different too much. Total number of cycles becomes very different. Frequency of the processor, about the same. So what really makes the difference? What really makes the difference? Right. So for this question, the same complexity, the same instruction count. And some of you might get this wrong because I think you really need to pay attention to the x86 instruction set architecture. So in x86 instruction set architecture, the move instruction, you can specify two index, column index and row index. So and if you look at what's inside this, there's actually no difference in implementing this inner loop. The total amount of loop iterations, the same. There's no reason why these two, they will have different instruction count. So the only thing that would make the performance difference is CPI. So for this question, only one question is correct. And it's an evidence as a programmer, even though this kind of subtle detail can give you like 5 times performance difference, right? So sometimes, right, as a trick, as a programmer in the very beginning, you should always deliver the feature to your boss and intentionally you write this kind of code and saying that, oh yeah, I got this feature done. And then the next month you say, I make a new contribution, I make the performance 5 times faster, right? Here's how you are going to make it happen, right? Now, another demo we have in the first lecture, can you now answering this question? All right, let's take a look. Okay, I love this figure because it really means that we need discussion. So why don't you guys go ahead, discuss with your new friends and see what do you guys think.
I know it's gonna help. It's just whether or not it knows whether or not. Right. I guess they would predict which way Johnny's gonna go. We're all trying to find a way to see it.
Oh. So you
I
think
think that's the fact that what matters is like whether or not. But I'm not sure if that's what the part that is why I guess the estimate is what
yeah.
I guess when you have all the different ones together, it knows how it's and it's wrong. You try to predict that wrong thing.
So it's still gonna jump.
Yeah, so it's not jumping. It's like this. It knows
Where to go, basically.
yeah. So I think instructions have it's work. It's work.
It's like we can execute more and like
All right, let's see what do you guys think after the discussion. So, very diverse. So most of you think it's D, but again, that's run a demo, right? Seeing is believing. So this is the code that we had, the same code as we have previously have, and this is so in this loop I'm calling this calculate sum and this implement this like order n, and this iterations is actually a constant number. So let's run it and see what do we have. And again, we are, do I have the, okay. So if you pay attention to the instruction count, like let's take a look. So this is the, let's see, we start with not sorting. So for the version of not sorting, we have this amount of instructions, and the execution time is about 0.55. And if we have, okay, so if you pay attention, like for the previous, for the unsorted version, we have 3 billion instructions, right? But for the sorting, it does add another 200 million instructions. So the sorting actually makes the instruction count, it changes the instruction count, but in a good way or a bad way. In a good way or a bad way? Bad way, because if you want execution time to be lower, you want the instruction count to be lower, right? So it actually makes the instruction count to be a bad way. But let's take a look at the CPI. So CPI is the flip of cycles per instruction, instruction per cycle. So it's 1/6. And for unsorted version is 1/1.33. So what does that mean? The CPI of the sorted version is a lot better. So programmer does change the IC, but not in a positive direction. And what the question is asking about? Made it better. I did made it bold-faced. You don't read it, right? So a lot of cases, it's not I intentionally make a trap. Is I already told you there is a trap. You still want to go inside, right? I already tell you that you should take CS203, but you still drop the course and you didn't get a job or you failed the interview question. That's your problem, not my problem. Right? I already told you better performance, right? So for this question in particular, CPI is what the programmer changes. Question?
But you can make it better without increasing the instruction count, right? It's like if you don't increase the instruction count, you don't get better. So in a way, it is for the better.
But we change the performance equation, right? So in terms of the interpretation of the performance equation, it's going to be worse, right? Okay. So one demo that I'm not going to show you is actually in your assignment. You are going to try this a lot. You can actually change the frequency of your processor through calling library functions. And here's the detailed document, and you can try that in your CS203 assignments, right? So programmers, you can control all factors in performance equation, and you determine the performance more than all other things. You choose the right programming language. After choosing the right programming language, you have to figure out what's the right way of driving that tool. So that's why CS203 is a computer science class, not an E class, because we really want to educate you guys to become someone who can write fast code. This is not a class about writing code faster. It is writing fast code. Can you hear the difference? Right? Okay. So a lot of software people, they thought if I have a good compiler, they would solve the whole problem. So now, for this particular code, if I turn on -03 on GCC, how many of the following can you expect? All right. Okay, I love this figure because it means that we really need discussion. So why don't you guys do it?
This bigger binary always be more instructions.
Yeah.
Oh, why do you think you would make the CPI lower for both of them? If you would for both. I feel like yeah, because like if it's a really common thing, then maybe
All right, let's take a look. So after discussion, okay, more of you think the compiler can do the amount of stuff, right? What's D? D, I believe, is 3, right? Like 3 things compilers can do. But let's take a look at what a compiler can really do. So again, seeing is believing. Wait, I think I got the wrong demo. Let me check. Okay, so okay, so this is okay. Let's try this. I think I should have everything here. So let's say we have this unoptimized version, and I'm going to use performance counter to see what the result looks like. And give me a second. Let me. Okay, it's right here. So this is again our. Okay, so I'm showing you how to debug your assignment. When you see this kind of error, it means that you missed one cell. So go to the very beginning, and then now, okay. So this is the same code, and again, we have the left-hand side and right-hand side, version A and version B. And this is an unoptimized version, and we all know the result. And now let's run different versions, and let's compare the result and see what the compiler optimizations can do. And let's show the result in a nicely rendered table and see what's the difference among different versions. Okay, look forward to it. So I have turned on different optimization flags, and in fact, like GCC right now have the -0 for. Let's take a look. In the very beginning, so again, like this is more like a sampling. So there may be some difference in numbers, but you should trust, like in the very beginning, as we show, that version A and version B, they have about the same instruction count. Now, and this is their CPI. The version A has a CPI 0.2. Version B has a CPI 1.2. And after applying -01 for version A, the instruction count goes from how many? 2 billion to only 403 million. Significant drop. How about the CPI? Drop? increases, right, from 0.2. However, when we talk about performance, it's the synthetic effect of instruction count, CPI, and the cycle time. So even though the CPI is higher, but because we have this very significant drop in instruction count, that's why the execution time is dropped significantly, right? For version A. Look at version B. How about this instruction count? From 2.5 billion to 600 million, not 400 million, right? How about the execution time? 0.6, is it faster? No. Compiler optimization never said we are going to guarantee your performance is going to be better, right? So if you said I turn on compiler optimization, my code must be faster, that's not always true. The instruction count for this version, right? Like if you check other optimization, 01, 03, 03, 04, they all have the same instruction count. The execution time is longer anyway. So what does that mean? What does that mean? This is a very meaningful example to tell you, even with compilers, why program still matters. Programmer still matters. Right? For code version A, we can gradually optimize it from 2.1 billion to 400 million to even lower, like 120. And I can tell you this is because the utilization of vector instructions. And performance can go from 0.08 to 0.03, 0.02. A lot of people, especially those people who teach software engineering class, they thought no matter what kind of programming language you use, what kind of like junk code, as long as it's easier to read, the compiler should be able to deal with it. You are going to get the same performance. And even though there is not super highly optimized, the performance difference is not that much. But look, 0.02 versus 0.61, 30 times difference. Compiler optimization cannot save you if programmer wrote junk code or unoptimizable code in the very beginning. So first of all, for this particular case, compiler optimization can reduce instruction count for both, particularly for this example. And in fact, for a compiler, it's the easiest metric to optimize with by using fewer amount of instructions. However, it doesn't always mean that the CPI is going to be better. The synthetic effect of instruction execution time doesn't necessarily to be lower. The most important thing, when compiler optimize your code, they don't want to distort what your original intention. So this kind of optimization, like flipping this order, they're not going to do that. So that's why, as a programmer, you think this is trivial. Sorry, it's not trivial, right? The compiler won't do that for you. So for this particular question, a lot of you thought like CDE, but actually the answer is B. Okay, so the last takeaway is compiler optimization does not always help, and it's based on some assumptions that may not be true on all computers. And programmer, your duty, or after you take TO3, we want you to be able to write code that can facilitate optimization. And most important takeaway for this class is that performance equation is defined by 3 elements, and programmer is the only one who can affect all 3 factors. And let's briefly talk about complexity. So I keep like trashing complexity and algorithm because I want to bring your attention. In fact, they are very useful. But why there is a mismatching between algorithm and complexity in real computer performance is because they also assume that we have a perfect computer in a way that every instruction takes exactly the same amount of time, every operation takes exactly the same amount of instructions. So that's never going to be true in any architecture. So that's why complexity algorithm in general, they are not reflecting your real performance. So complexity does not provide good assessment on real machines because it's idealized assumptions. So before you leave the classroom, several important things that I want to let you know. So first of all, program assignment due this Thursday, and assignment 1 already released. And when you submit to Gradescope, make sure that you submit the correct item and watch the video before you start the assignment. And because originally I put the wrong lecture time in the calendar, so I adjust the office hour schedule. So for Tuesday, Wednesday, 1 p.m. to 2 p.m. is my office hour, and our TA has a remote office hour on Zoom for 4 p.m. to 5 p.m. and Thursday, 2 p.m. to 4 p.m. on in Winston Chong Ho 110 to better assist you for assignments. A lot of questions you guys ask, it's not easy to address on the email, and some of them we do really need to see what's going on in person to get that out. And make sure that you finish the reading quiz course agreement before taking this course. And there's another reading quiz due next Tuesday, and we will drop your least performing reading quizzes, 2 of them. And another thing is that I know this is probably the first time you guys use Parallel Learn, and there was a feature that we could not control, is that once you close, you cannot restart, because the purpose of Parallel Learn is that they want to be a computer-based testing system, and that's exactly the same system you are going to use for your midterm and final in the testing center. So that's why we use reading quiz for you to get familiar. And later on, you are the 2 weeks later, we are going to let you schedule a practice exam to get familiar with the environment of the testing center, because when you take your midterm and final, you are only allowed to use their computer. So, and to be honest, I have no idea what their computers look like, what their environment look like, so check that out for you. And check the website for slides, quiz link, and Gradescope to submit your assignment, Discord for discussions, and we periodically upgrade, upload your grades, and this is the only place you can find the most authentic answer to how are you performing in the class. And we publish all the lecture videos on YouTube. Other than that, enjoy the rest of your day. I will see you on Thursday.